An example, for example, this is a strain gauge example that is being shown over here, okay, in this once again from the book. So this is, for example, you are sensing something. This is a strain gauge that is put on a cylinder, for example, and the cylinder is undergoing some kind of a tensile loading in this case. So this is a strain gauge. Same examples happens everywhere. It is connected now to a bridge. Okay. So this is your conversion part. Okay. Then it goes to an amplifier filter. Filter, we already know what it is. This is the conditioning to remove extraneous signals and stuff like that, and also to amplify the signal. And then subsequently this data is passed on to a DAQ or a DAC. Okay, so this is conditioning and storage. There is storage. Okay, so and this part is basically transmission. Okay, so strain gauge is a sensor whose electric resistance is sensitive. So here the resistance actually changes when you actually stretch it. Okay, and therefore when as you elongate, it gets stretched. As a result of that, you can sense it. It changes. This is wired now to a Wheatstone bridge, which we call bridge over here, which converts the change of resistance into an electronic voltage. Okay, so further use of an electric amplifier and a low pass filter, in this case it is a low pass filter, that conditions this voltage to a measurable low noise electric signal, which is subsequently transmitted to a DAC, or it can be displayed even on a computer, whatever it is that you want to do. It can be also used for further analysis. Okay, so this is the way that this actually happens. So this, you can see all the parts how this is done. So what is transmitted is basically a low noise signal. Okay, so this is where it is converted to voltage. Right. So as you can see, so this is a very nice operation. So similarly, you can have static response and static calibration. So static response and static calibration. Okay. So the operation of a measurement system is called static when all its inputs and outputs are either constant or varying very slowly with time. Okay. So you have a measurement system, say all its inputs are not a function of time. So inputs are not functions of time, and whatever output that you are producing is also not a function of time. Even if it is a function of time, it's a very slow function of time. Okay, so what happens is that as the input changes, the output changes, but they are not time dependent. Okay, so this is what is called a static response. The relationship that provides a value of the input as a function of the system output during this static operation is called a static response of the system. So static response, okay, response during static operation of a system. All right. So static calibration is preferably performed separately for each desired input. Okay, so that means you provide all the inputs and then you know what are the static values. Okay, so the values of this input are measured independently by some other instrument whose response is known. So we are trying to see that what is the one-to-one mapping between the input and the output in this particular case. Okay, The values of the input are measured independently by some other instrument whose response is known and and that serves as a standard. Sometimes it is impossible or difficult to maintain all but one input constant because changes in the desired input may trigger changes in other desired inputs as well. So that means there is some sort of a coupling that goes on between the input. Okay? In such cases, all changing inputs must be measured during calibration and different effects must be identified and separated. Okay? All possible interfering and modifying inputs during calibration should be maintained at the same level. The undesirable inputs may distort the static response. Okay? So if you have an undesirable input, okay, what it will do is that it will distort the static response. By introducing what we call drift, zero drift, okay, namely which is a parallel shift in the calibration curve, or a sensitivity drift, which means a change in the slope of the calibration curve. So if this is your calibration curve, so a drift could be like this. So this is a zero drift, or it could also change this, which is basically a sensitivity drift. All these undesirable inputs can actually do that. This is input output, or rather this is input, this is output. This is input output calibration. Okay? So for example, there are two types of static response. Consider the measurement of a pressure difference between a gas using a liquid manometer and a variable reluctance pressure transducer. In the first case, the input is related to the difference in height determined by the hydrostatic law. Okay? In the second case, the same input is correlated to the electric voltage by certain approximations. So for example, you want to measure the pressure difference. The P1 minus P2 is the pressure difference. Pressure difference is what you want to measure. Now this pressure difference, what you want to measure, you can do it by using a liquid manometer, okay, or a liquid manometer, or a variable, pressure transducer. This is the premise, right? So how does a manometer do? A manometer is pretty simple. It is P1 minus P2 is equal to rho L E into delta H. This is what the manometer will do. Okay, so rho L is the liquid density. Okay. In the second case, this is what the pressure transducer, what the transducer is going to do. It is going to measure the same thing but by an electrical means. It is alpha E plus beta, where these are calibration constants, which is measured through calibration. But this is done by the calibration of the transducer using a manometer. Okay, so the transducer is calibrated by a manometer, because what it measures is basically the electric voltage. So this is the electric voltage. Okay. So this also measures by a strain gauge. There is a strain gauge in between which gets deflected and which leads to that. Okay. So the static sensitivity is the slope of the input output relationship. If you put it like this, static sensitivity, basically the slope. So if you have an input output, this is the slope, okay, of the, so this will be the slope. So these curves can be anything. It can be like this also. So the slope may be a variable slope also. Okay. So if it is a linear slope for a linear system, for example, the slope is constant, whereas nonlinear systems will have a local sensitivity which varies with their input range. Okay, so this might have different slopes. So static sensitivity is good. Then let me quickly say that there is something called scale readability, which refers to analog instruments. Is the minimum change in output that can be recognized by an observer. This is also, of course, subjective. Then the span of the full scale is a range of input that the measurement is designed to measure. And then there is full scale output, which is the algebraic difference between the output values and the maximum and the minimum input values. In the dynamic range, I think this one, I'll write it down. The dynamic range is basically the ratio of the largest to the smallest values of the input. Largest value of the input divided by the smallest value of the input. Okay, this is what the system can measure. The linearity is the maximum deviation from this linear scale. So linearity is a measure of actually non-linearity. So any deviation, so the manufacturers specify linearity as a percentage of the instrument's reading. So threshold is the smallest input level that will produce a detectable input. The threshold is the smallest detectable, smallest input level that is detectable. Okay, that is detectable. Okay. Similarly, the resolution will be something, you know, that is the smallest input change. The smallest input change. Okay. Smallest input change that will produce detectable output change. There can be also features like hysteresis. Okay, the hysteresis is the difference between output value corresponding to an input value. The difference between output minus the input. Okay, so output value that was reached while you are going up versus going down. Okay, from below and from reached from above. So if you go from point 1, point 2, and then if you come back like that, so that is something like an hysteresis. Okay, so up or down. Okay. And then of course you have other things like normality tests and removal of outliers and stuff like that. There will be some values. By repeating the measurements, you want to check whether all these values are constant or not. So there are normality tests. Beyond, we are not going to go into the details for that. You can also identify trends by looking at a process under statistical control. So you can do all this, then curve fitting, linearization of the data. There are lots of things that one can do. Okay, and all these things you can check. So there are also, let us just quickly look at the dynamic, because this is not a full-fledged measurement course of that kind. So you can read up all these things from the book. So the dynamic response of measuring systems. Okay. So operation of a measuring system is called dynamic if at least one of its input is time dependent. Okay, it can have multiple inputs, but at least one has to be time dependent. So unlike static response, which is usually prescribed by an algebraic relationship, the dynamic response is generally specified by a differential equation. So dynamic response is specified by a differential equation. Okay. The dynamic response of systems is usually modeled by, therefore, is modeled by mathematical equations describing the physical principles like circuit laws, momentum balance, or energy balance, An output depends on several inputs. The full mathematical model would likely be a set of nonlinear coupled partial. Okay, so stuff like that. So let us look at a few of them, like a zero order system. Okay, so zero order system is characterized by a single parameter. Say, for example, y equal to kx, where the static sensitivity is k. K has the same dimensions as the ratio of y over x. The dynamic response of a zeroth order system is independent of time. Okay? The dynamic response, you should say, response of a zeroth order system okay, is dependent of time. Okay? The output remains proportional to the at all times. Okay? So output and input remains proportional to other. Okay? Examples of this zeroth order systems are electric resistors, elastic spring, okay? So these are examples of zeroth order systems. Okay? Then you go to the first order systems. This is first order. Okay? So what are first order systems is like tau dy by dt y is equal to kx. This form is characterized by two parameters. One is the static sensitivity, okay, and the other part is basically the time constant. So the examples of such systems will be the resistor, capacitor, systems, for example. Then there will be second order systems. So see here the time constant comes. The second order system is characterized by three parameters, the d square y by dt square plus I omega y by d plus omega square y equal to k. So one is basically, once again, this is the static sensitivity. Okay. And then there is an undamped natural frequency. This is undamped natural frequency. Okay. And the last one is basically the damping ratio. Okay. So this a second order system is called undamped. So this system is called undamped when equal to 0, and it is called critically underdamped. Okay, damped when this is 0 less than 1, and then the last one is critically damped. So there is an overdamped also. Critically damped when this is equal to 1, and overdamped when 1. Okay, so these examples of this that can be represented is a liquid manometer. So one type of a system is a liquid manometer. Okay. We will see why these will be important, because PIV, when we actually do PIV, for example, you will see whether the particles, what kind of a systems they are. Okay. How do they respond to the flow? Okay, so with the exception of zeroth order systems, the output of all other systems exposed to a time dependent input depends not only on the current value of the input but also on its time history. Okay, for the description of dynamic response, it is customary to consider a few idealized type of inputs. Inputs. So let us consider the types of inputs. Okay, this will come in handy, as I said. So when you actually have a relatively fast, so this can be anything. This can be velocity. This can be anything. So it goes for, say, t less than 0, it was this. For t greater than equal to 0, it becomes equal to 1. So it's a relatively fast change of the input from one constant level to the other. It is like a unit step or a Heaviside function. Then a sudden impulsive application of a different value of the input. So lasting only for a brief time period can be also idealized as a unit impulse function, a delta Dirac function. So this is like a Heaviside. Heaviside function. Then you can have situations where your delta t is equal to 0 for t less than equal to 0, delta t approaches infinity for, say, t greater. Okay, so the idea is that minus infinity to plus infinity, if you have a delta x to dx equal to 1. So this may be idealized as proportional to you can have a sudden impulse and then can last for a few, for a very small instant before it returns the original level. You can also have a gradual change. So this is for an impulse. For more gradual change, okay, starting from a constant level and they persist monotonically. Say, for example, RT is equal to 0 for t less than 0, then it is equal to t for t greater than equal. So something like that. Okay. You can also have periodic functions. A function can be periodic. Okay. So that you can also have, say, periodic function. Let's write that. So okay, where your ft is basically is equal to f plus nt, where n is the integer number. Time period. Okay, so this is the period, right? So you can see all these nice little features. So you can do, and then you can also now calculate the dynamic response for first order systems and second order systems and stuff like that. Okay, which you can read once again from the book. Okay, I am giving you heads up that you can read. There is a lot of materials in the book. You should read chapters on step response. So the dynamic response, say, of a first order system, response of first order systems. So you can have a step response. You should read this from the book. Step response. Okay, so it's something like xt is equal to aut. Remember, ut is the function that we just now. Then you can also have an impulse response. Impulse response, where your xt will be now equal to a delta t. And you can now calculate that what will be the dynamic response of the first order systems, how the system will respond to changes like this. Okay, then you can also have a ramp response, which is basically a monotonic one, is RT, which we just now did. Okay, and you can also, so these will be the kind of responses. Then you can also go to the response of the second order systems. Okay, And there also you can do the same thing for step response, or dynamic response, for impulse response, and ramp response. Okay, all these things, and then you can go to higher order and highly nonlinear systems, and you can also use things like the Laplace transformation. See that how these responses, how the time dependent responses can be analyzed. So these are kind of you can read from the book. Okay, and there are lots of things that one can do, but you can also do the same thing here for the second order systems. There is no time to do the math, but you can try the math, and then you can also go to higher order systems, see how Laplace transforms and other things actually help. So we talked about static response, we talked about dynamic response, we talked about what the measurement system is, what are the sensors, how the sensors needs to be calibrated, how the sensors can actually, how there can be interfering signals from all over. Okay, and also, which what we did not cover again is something that you should read. You should read about the tests, the data test and the curve fits that are part of this particular exercise. So the book that one should read in this context is Measurement. For this part, Measurement in Fluid Mechanics by Stavros. This is a very good book published by the Cambridge University Press. I covered the fluids lecture and this lecture from this book. So this is a good start which you can have. You can go through this, and I've just given you some ideas of the different measurement systems, because this dynamic response and other things will be needed once you try to analyze systems, particularly using PIV, even with hot wire anemometry, and even if you want to take point measurements like temperature using a basic thermocouple, that is also something that you can cover as a part of this book. Okay? So the choice of, so we have covered a lot in fluid mechanics as well as measurement systems. Okay, we have also seen how the systems actually respond. Okay, even though we did not go into the math part of it, so to say. Okay, so there will be a lecture on signal conditioning and image analysis, because we are not going to cover all of these things. This you are supposed to read up from the book. Okay, that how, for example, measurement uncertainty, measurement errors, stuff like that. These are some things that you should learn by reading from this book. Okay, we are going to cover just the image analysis and the signal conditioning part in the later section of this particular course. So we stop here before we move to the measurement techniques now. Okay, and not measurement, first look at the imaging and the optics part, and then go on to the measurement techniques.